Let us look at the third theorem of isomorphism. It says, let G be a group and let N be a normal subgroup of G and H be a normal subgroup of G, with N being a subset of H, which is in turn a subset of G. Then the quotient group formed by the quotient groups, that is G by N by H by N, is isomorphic to G by H. Okay, so let's see what this actually means. So let's say we have a group G. We have the quotient group G by H. We have the quotient group G by N. And we have the quotient group of quotients. Then there is a isomorphism here between G by N by H by N to G by H. So let's prove this. So since N is a normal subgroup of G, we can form the quotient group G by N and let pi sub N be the homomorphism between G and G by N. Similarly, since H is a normal subgroup of G, we can form the quotient group G by H and let the canonical projection pi sub H be the homomorphism from G to G by H. So again, let's bring in that in the diagram. Inside G by N, the subgroup H by N is normal because H is a normal subgroup of G and N is a subset of H. Now let phi be the homomorphism from G by N to G by H, where phi of Gn coset is equal to coset Gh. This is what we are talking. Phi is the homomorphism here. We have to make sure that phi is well defined. So if G1n is equal to G2n, then G1 inverse times G2 is in N, which is a subset of H. G1 and G2 are the elements of G. Okay. Hence, G1H is equal to G2H, which implies phi is well defined. So think of it carefully. We are taking two elements from the group G and forming cosets with N, the elements of N. Then, if they are equal, then G1 inverse times G2 is in N, which is a subset of H. Since N is a subset of H, we can say G1H is equal to G2H, which implies phi is well defined. Now let's see homomorphism. Again, phi of G1n times G2n is equal to phi of G1 times G2 times n is equal to G1 G2 H. Because remember, again, n is a subset of H, which is equal to G1H times G2H, which is equal to G1H is phi of G1n and G2H is equal to phi of G2n. So the product of these two can be written as the product of this homomorphism, phi of G1n times phi of G2n. So which means phi is a homomorphism. Now let's look at the kernel of homomorphism. Here kernel of phi is equal to the set of cosets Gn in the quotient group G by N, where phi of Gn is equal to H, which is equal to the set of cosets Gn, where Gh is equal to H, which is equal to the set of cosets Gn, where G is in H, which is equal to H by n. So each of these steps you need to be very careful in understanding. So that means kernel of phi is h by n. Now let's look at image of phi. For any coset gh in g by h, we have gh equal to phi of gn because of this homomorphism, which implies image of phi is equal to g by h. So phi is a surjective homomorphism with kernel h by n. Now let pi be the homomorphism from g by n to the quotient group of quotients, that is g by n by h by n, be the canonical projection. So now we started off with all this, but now we can just focus on this part. Yes, g by n is a group, g by h is the image of phi, and h by n is the kernel. Are you able to map it to the first theorem in your mind? So we apply first isomorphism theorem. The group is g by n, image of phi is equal to g by h, kernel of phi is equal to h by n. So, which implies there exists an isomorphism g by n by h by n to g by h. This one. So, we have proved the third theorem of isomorphism. By the way, if you remember, in the second isomorphism theorem also, we use the first isomorphism theorem. In the third also, we are using the first isomorphism theorem. So, the first isomorphism theorem is also called the fundamental theorem of isomorphism. Okay, now let's look at an example to understand this better. Okay, so let's take G is equal to Z sub 24 under addition modulo 24. Let's take a normal subgroup of G. Remember, Z sub 24 is a cyclic group, which means you can choose any generator. All of them will generate a normal subgroup. So here we are taking 12 as the generator. So n equal to the generator 12, which will generate 0, 12, which implies that the order of n is equal to 2. Again, H also has to be a normal subgroup, cyclic group, so no issues, we can choose any. So here we are taking H equal to the subgroup generated by 6, which gives us 0, 6, 12, and 18. So the order of H is equal to 4. And notice that N is a subset of H, and H is a subset of Z sub 24, that is G. Now let's form the quotient groups. G by N is equal to Z sub 24 by the subgroup generated by 12. Now this has an order of 24 by 2. 24 is the number of elements or order of Z24, and 2 is the order of the subgroup generated by 12. So 24 by 2 is equal to 12. So G by N is isomorphic to Z sub 12. Okay. What about H by N? Quotient group is equal to the subgroup generated by 6 by subgroup generated by 12. This has the order 4 by 2 because 6 will generate 4 elements. 12 generates 2 elements. So 4 by 2, which is equal to 2. So H by N is isomorphic to Z sub 2. Okay, so we have seen G by N, we have seen H by N. Now G by H. So G by H is equal to Z sub 24 by the subgroup generated by 6 has the order 24 by 4. 4 elements generated by 6. So 24 by 4 equal to 6. So G by H quotient group is isomorphic to Z6. That is the set of integers under addition modulo 6. Okay, so now we have G by N, we have G by H, and we have H by N. So LHS in the theorem, LHS is G by N by H by N. So G by N by H by N is isomorphic to G by N is isomorphic to Z12. So Z12 by Z2, which is H by N. And if we take this quotient group, we get something which is isomorphic to Z6. What is G by H? That is isomorphic to Z6, which means LHS is isomorphic to RHS. And hence, G by N by H by N is isomorphic to G by H. So that was third theorem of isomorphism. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.